Okay, but before we start, I would like also to share the books that we're using. This one. Okay, so yeah, so this is the book that we are using. Uh, it's called this one, yeah, the transfer phenomena. And then today we're gonna talk. So if you look at the book, you can see that the first part is the momentum transport that we're gonna talk in this a few weeks. And then last week we talked about viscosity and then also mechanism of momentum transport. If you're curious, you can also read, but it is I'm not gonna explain it a lot, but you can have a read, and then you can check maybe the viscosity in a gas or in a liquid if you're curious about it. And the viscosity is a function of temperature. You can have a look at this one here. And then we also talk about the convective momentum transport. And then today we're going to talk in chapter 2. Yeah, so you can have a look in the chapter 2 here. And then and then last week we talked about a shell momentum balance and also the boundary condition. So I really strongly suggest you have this book and then also read the book, and then make a mark, make a note, yeah, because usually the exam is it can be open book, sometimes it's closed book, of course. In here you can see, for example, this is the picture that I copy, yeah, in the presentation, and also uh, the momentum balance, which is the rate of momentum in by convective transport and also by molecular transport, minus the rate of momentum out by again convective transport and molecular transport, and the additional of force gravity, if any, acting on the system. And in the page this one, yeah, in the page 41 and 42, you can also get the procedure, how to setting up the viscous flow problem. And also around here, in page 42, this is very important, you may want to make a highlight here. This is the most commonly boundary condition. Yeah, okay, okay. So this one is most commonly a boundary condition. Yeah, okay. Yeah, this one. So the first one, at a solid interface, a liquid-liquid interface, and a liquid-gas interface. Okay. And today we're gonna continue our discussion regarding the uh, example in chapter 2.2 about flow of a falling film. Okay. And in a flow of falling film, you can, maybe you can see some example, for example, in a not waterfall, yeah, but uh, maybe in some water fountain or something like that, or a column, yeah, in the uh, yeah, some water fountain like this. So here you can see that again, this is the liquid films, and then we would like to have a look about this one. Okay. And here also I did highlight this one like few years ago because this is important. So here, for the small rates, we expect that viscous force will prevent continuous acceleration and liquid down the wall. So the Vz would be independent of z, in short, a distance down the plate. Okay, so I really strongly suggest that you have this book and also read this book. This is quite old book, about around 670s, but Bird et al. Is the really basic foundation for the transfer phenomena. All right, so now I'm gonna stop share, and then let's continue our discussion for today. Okay, so maybe I can make it bigger like this. So let's have a look about uh, the the schematic that we talked last week. And then so here we have the boundary condition, we have the liquid or falling film there. And so what we need to do is first we have to where is it? So first we have to construct uh, so if we look at the procedure, let me check again the book here. Okay, so first is identify non-vanishing velocity and variables. Okay, so we have done that before, so we know that phi z, we have the phi z, but it is a function of x. Yeah, so here the phi z is actually a function of x. That means the phi z, phi in the direction to the z, is only changing if the x is changing. Okay, for example, around this one on the wall, the phi z would be equal to 0 because here is on the plate. But however, around the surface here, the phi z would have a value for that one. Okay, and then how about phi x? Do we have phi x? V, that is the velocity that actually that moving to the x-axis. Do we have a fluid moving to the x-axis? Do we have Vx?
No.
No. Okay, good. Do we have Vy? V to the y-axis. So that means, yeah, the fluid goes that way. Do we have Vy?
Also no.
Oh, because all of the, if you think about it, all of the fluid will just flowing downwards that way. Yeah, so there is no uh, flowing that way. What happened? So for example, what happened in the case if v is a function of y and a function of x? So that would be there would be a swirling. Yeah. If you remember, if you have, for example, if you have vx, and then if you have v to the y, then what happened, you will have a resultant of a vector, then that would be like a swirl. Yeah, okay, there would be something like that. Okay, so that would be okay. So we've done that. And then the second one, we have to write momentum balance. Okay, so this is the one that we have to write. And then here, okay, so this is the momentum balance. Yeah, there. So the moment, so this is also this is called the shell. Okay, the shell start from x to the x plus delta x, and then from z equal to 0 to z equal to L, and from y equal to 0 to y equal to L. Okay, so this is this thin shell. That's why we call shell momentum balance. Okay, so first we have to identify the it's actually equal to the momentum in, yeah, and the momentum in the, if we talk about c or about c, it is called flux. It's called momentum flux. So if we want to calculate it with the momentum balance, we have to calculate it with the area, the area that is perpendicular to the direction of the momentum. Okay, so for this one, so let's have a look on the here on the CZZ. So CZZ means the momentum from z, yeah, to the direction of z, caused by the velocity of Vz. Okay, so we can write it as Cz, and then that should be multiplied with the area. So what is the area for this case of the Cz? Can you try? So the area would be the length of this y or w multiply with delta x. Yeah. Okay. So this is w multiply with delta x. We called it in when at z equal to 0. Okay, and then we can write the out one. So c z z when z equal to l with multiply again with the w dot x. Okay, that is in this side. Okay, and then this sides. Okay, and then plus c x z. Okay, so cxz is actually the momentum to the x caused by the velocity of v. Okay, and then if you look at here, so the area, the perpendicular area for the xz is the, if you look at it, so the area here is the, can you help me? What is the area for xz?
W times L, Bu.
W times L, yeah, L at equal to x, yeah, and then minus c xz when x equal to x plus delta x, yeah, that will be same as well. Multiply again that lw. Okay, and this one, and then if you want to add, you can also add this one, cxz, sorry, cyz there, and also the outer one. But I'm actually gonna just delete it because I know that vy and vy is 0, so this one is 0, and tau yz also 0 because we don't have the z divided by dy, yeah? We don't have a difference for the here, so that equals 0. So I think I'm gonna neglect this one. Okay, and then plus with the gravity. For the gravity, we have to calculate the rho, yeah, which is the density, multiply with the volume. And what volume? The volume is the shell, yeah, the ruang tilik, the shell that we're looking at. So if we look at the volume of the block, that means would be w lw multiply with delta x. Okay, and that's equal to 0. Okay, so I think it is very good idea for you in your paper, in your books, write it, yeah, and then try to do it yourself. So the momentum balance, the equation for the momentum balance from the momentum in multiply with the area, and then here and out, and minus in and out, and then plus the gravity acting in the system. Okay, in the book it is written here, and then here okay, don't forget the rho mu, yeah, rho multiply v and multiply the gravity. Okay, and the gravity here, because here the gravity we should look at in this area here, so the gravity should be this one there. So this is the gravity, so we're gonna looking at the gravity cos beta, yeah, the cosine of beta, so multiply with gravity cos beta. Okay, so here in here you can also read or rewrite again the rate of z momentum across the surface equal to 0. Here the input, and then this one is the output, yeah, the out at the momentum across the equal to L, and then here is the momentum in across the x, and this is out, and also this is the gravity acting fluid on the z direction, again because the one that we're looking at is in the z direction. Okay, so when these terms are substituted into a z momentum balance in this equation, and then we can get this one. Okay, so here this one is the same, yeah, L and W, L and this is also a W and X, and this one in here. Okay. So and after that, and then we can have a look. We can try it here, and then what we can do, we can divide all of them with L, W, and delta X, yeah, at the same time. So all of them, we divide it with L, W, delta X. That is to simplify the equation. Okay. So here, if I can write it out, so let me continue in a paper here. So wait. Okay, so once we get, okay, yeah, this one, yeah, so we have the equation. So once we delete that one, when we divide them with L, W, and delta X, then we end up with C x z at X minus C x z at X plus delta X. This becomes, is divided by the delta X, okay, and then plus C z z equal to 0 minus C z equal to L, multiply with, because this is divided by W and delta X, so this equal to L, yeah, and then plus L, W, delta X is diminished in the previous one, yeah. Here is all of them is diminished, so it becomes rho g cos theta, rho g cos beta. So I'm gonna write equal to rho g cos beta. Okay. Now in this case here, so now let's consider this one would be equal to delta X would be very small, is equal to L. It will it's equal to 0, sorry. So then this case, this one is become, sorry, keep. Okay, so this one, yeah, this one is become a limit. Yeah, that would be become a limit. So then we can write that d of C x, maybe I can write the other one later around. Okay, so limit x delta x equal to 0 of the this one, maybe I can write C x z divided by x minus C x z divided x plus delta x divided by delta x, okay, plus this one. Vz z equal to L divided by L plus rho g cos beta. Okay, if you remember about limit, so if you have a limit delta x equal to 0, function of x plus delta x minus function of x divided by delta x, that would be equal to the derivation of this one. Okay, so then here we can get this one equal to minus d c x z over dx, okay, plus c z equal to 0 minus c z plus equal to L plus rho g cos beta divided by L, okay, equal to 0. Okay, that one is the equation. Now the problem is okay, so we have derived this one. Now the next step that we would like to check is what is this C, or this is the combined momentum, right? And this is the combined momentum. Okay, so what we can do is to try to to expand the combined momentum for each part. So for example, okay, let me, okay, please help me. So what is the uh, so here what is the C x z is equal to the um, mu, yeah, plus the tau, yeah, so that would be equal to chronicle delta of ij multiplied p plus uh, the remember I can check again, so that would be equal to, wait, yeah, that one, and then plus uh, rho phi x phi z plus tau x z. Okay, remember from last week. Okay, so the psi xz equal to the momentum flux in molecular one sorry, not this one, psi plus, it should, no, it should be, okay, so it's equal to, yeah, that would be that one, yeah, there, so that would be the psi plus rho phi x phi z, and the psi is actually equal to uh, the momentum flux for the diffusion one, yeah, and then the molecular flux equal to the pressure, and also to the this one, yeah, the viscous force. Okay, do we have a p in here? Because the chronicle delta is not equal to 1, yeah, it's not similar, ij xz, yeah, so then we can make it, this one is equal to 0 for the p, so there is no pressure, yeah, there is no pressure force, there is no tidak ada gaya tekan. Okay, and then we have rho phi x phi z. Do we have phi x? Do we have phi x in here?
No, I don't think so.
No. Okay, so because this is 0, so then this would be equal to 0, and this also equal to 0. So then the psi xz is actually the one that contribute to psi xz is actually only the tau, yeah, or the momentum flux, or the shear stress. Okay, so this one, so that means this one we can change it with the tau xz. Okay, and then let's check another one. Now let's see about the PZZ. Okay, let's see the PZZ here. And for the PZZ, we will have the pressure, yeah, because chronicle delta is I equal to J, yeah, so it's in the same direction. And then we also have equal to, what is this, the tau z, yeah, because here, okay, so there's a pressure, gaya tekan, the viscous force, and plus the convective momentum transport, or rho v z v z. Okay, now the question is, do you know, do we have the pressure? If there's any pressure on the CZZ, we have pressure, yeah, we have pressure, of course. Okay, this also, how about tau ZZ? Do we have tau ZZ? So if you think about it, tau z is actually minus 2 mu d phi z over dz. Do we have a difference between d phi z divided by z? Do we have a difference of the velocity in this direction, in the z direction? Ada perubahan
Uh,
kecepatan pada arah z?
no, I don't think so.
No, yeah. So this one would be 0. Karena tidak ada perubahan kecepatan pada arah z. Okay, so that means around here the CZZ equal to 0. Okay, do we have a rho phi z? Yeah, we have phi z, yeah, we have rho. So we have this number and we also have this number. Okay, now the problem here that we would need to looking at is the CZZ is equal to 0 minus CZZ equal to L. Okay, now so we have to make a difference. So we have to subtract them, the pressure at z equal to 0 minus P when z equal to L. Now, the pressure in z equal to 0 and also z equal to L, is it similar or not? Okay, we can have a look on the previous one. So here, let me try to draw. Yeah. So here we have pressure. We also here we have pressure. Okay, but because the system is open, system terbuka, yeah. So the pressure around here that would be similar with the pressure around here. Got it? Tekanan pada ujung sini akan sama dengan tekanan pada ujung bawah. That is because the pressure is the system is open, it's atmospheric, so the pressure that we got in this case would be all the atmospheric pressure. Okay, so then we can conclude that the pressure is actually the same at z equal to 0 and z equal to L. Okay, why is that important? Because we have to know the value. Yeah, the value, is it different or not? Okay, so okay, I'm gonna maybe just do okay, so maybe open that one there. Okay, so we have the pressure, so but the value is similar in here and here. Okay, the second one, in here we also have rho phi z. Okay, the value of phi z in z equal to 0 and in z equal to L, is it the same or not? The value of phi z.
It's the same.
Why is the same, Kevin?
Because there is no change in X rate.
There is
Because VZ is equal to VZ X rate. There's no derivation.
no change of phi z in the z direction. Yeah.
Yeah, I think so. Wait.
Yeah. Okay. So, because there is no change in phi z in the z direction, so that means the value is the same. So if you subtract the similar value, then this one would be equal to 0. So if I can write it in different color, so here the P plus rho phi z minus P plus rho phi z, yeah, this one, that's also the same. So this equal to 0. So this one, this area here, that would tell you that would be equal to 0. Okay, so that so because of that, now yeah, so here I think you can so this is how it's written. Yeah, so that we write the component there. Yeah, we have the P and Z. So again, this one is equal to 0, so that only become that one there, and here is only become phi z is there is the number there, but the difference would be equal to 0. So that actually conclude that the one that we have, it becomes, yeah, so if you look at here, back to here, here, so I think I can, maybe I can just add some more slide in here. So I think I can write it here, yeah, so it would be easier. So the one that we have here, now we end up with minus d. We have to change the psi of xz. Oops. We have to change the psi of xz with or maybe I can make it like this, yeah. So let's change the value of psi xz with this one, yeah, because this one equal to 0, this one equal to 0, so this tau, okay, and this one, this area for the psi zz would be equal to 0, and then here we have the contribution of rho g cos beta. Okay, so with this one we can simplify, that would be become d tau xz over d x, is it, yeah, plus rho g cos beta equal to 0. Okay, or if you want to make it in the other side, then we can just multiply both sides with a positive and then just rearrange that one over the other. Okay, that one there. Okay, so this is called the differential equation of momentum flux. Okay, now to know the profile of the momentum flux, what we can do is we can do integration. Okay, to do the integration, we can integrate both sides, and so this become tau xz d tau xz equal to rho g cos beta dx, and we integrate equal to rho g cos beta multiplied with x plus a constant, and this constant means the boundary condition. Okay, so here, so there is a C1, so that means we have to find boundary condition. Okay, now so go back again to the previous slide where there is some boundary condition there. Now the one that we would like to see is what is the boundary condition related to the phenomena, and then it's related to the flux momentum. Okay, let's have a look there. So again, the first step to see is maybe we can check again this one to the flow of falling film. What is the boundary condition that may be related to this schematic, yeah, this phenomena, and related to the flux momentum? Okay, in the previous slide, or maybe it's better if I just close this and let's have a look on the previous slide. Where is it? Or maybe in here, yeah. In the previous slide, is it this one? Oh, this one. Okay, in the previous slide, if you remember that this one, yeah, so this one is the this is the commonly used boundary condition. Yeah, there are commonly used boundary condition, which is at a solid fluid interface, the fluid velocity equals to the velocity in which the surface, the solid surface is moving. The second one, liquid-liquid interface, we don't have liquid interface. And look at the third one, yeah, the last one, where is the at liquid and gas interface, which is we have the stream, and then this is the atmosphere, yeah, which is the gas. And then the stress tensor component tau xy and tau xz are taken to be 0 because at that time the shear stress is very low. Gaya gesek sangat-sangat rendah between the liquid, between the fluids and also the gas. Okay, because the stress or the shear stress is very low, we can assume that the tau xz would be equal to 0. Okay, so this one, the tau xz equal to be 0, this can be our boundary condition. Okay, so this can be the boundary condition. Okay, so then we can go back again to the previous one, which is this one. Yeah. So because we have to find this one, the boundary condition, we can write that at okay, so at x equal to 0, yeah, which is on the surface, because if you remember in the previous one here, this is the boundary, this is the on the surface. Yeah, on the surface is actually when x equal to 0. Okay, this is when x equal to 0 there on the surface. Then the tau xz equal to 0 because the shear stress gaya geser sangat rendah between the water and the atmosphere. Okay, on the gas, that one. So then we can write up to here as x equal to 0, the tau xz equal to 0. Okay, so the mathematically it is easy to solve, but the one that I really want to emphasize to you is the concept behind it. Okay, so tau xz equal to 0, so this is 0 equal to 0 plus c1, so then we can conclude that c1 equal to 0. So therefore the equation would be this one, tau xz equal to rho g cos beta, yeah, rho g cos beta multiplied with x, and this is called the momentum flux profile. Okay, so that's it. So if you're asked, so for example, derive the equation so you can get the momentum flux profile of the phenomena. So this is the momentum flux profile. Okay, now once we got this one, so here this one, so yeah, so this one, so see the momentum flux profile or the momentum flux distribution is tau xz is equal to rho g cos beta, which is, this is a number multiplied with x. So if I want to draw the schematic, yeah, if this is let's say this is the flow of the falling film there, and this is when x equal to 0, this is x equal to delta x, we can try to check. Yeah, so at x equal to 0, there would be no there is no flux, momentum flux distribution, tidak ada gaya gesek. But when x equal to L to delta, let's say the thickness is delta, the tau xz would be, there is a number on that, which is rho g cos beta multiplied with delta, or maybe around this one. Okay, so this is gonna be the profile for the momentum flux distribution. Okay, so we can have a look. So here is at on the surface we have the highest momentum flux. Kita punya gaya geser yang sangat tinggi, paling tinggi, and there is no shear stress on the surface. Okay, now to get the so that is the momentum flux distribution. The next part is how to get the velocity distribution. So what we can do is we can input, or we can substitute the Newton's law of viscosity into the equation. Okay, so we have the C exit equal to rho g cos beta x, and then let's just substitute this one, the Newton's law of viscosity, into the flux momentum, which is mu minus mu dv z over dx, rho g cos beta, and then with some x there, and then you can rearrange them into here, so dvz over dx. So this is the differentiation of equation for the vz is function of x, and then let's do the integration for both sides. This is x, so that become x squared, and then half x squared there, and then with the plus the another boundary condition. Okay, so for the boundary condition, we can use the second one, which is at the non-slip boundary condition. So that means at the non-slip boundary condition, let's check the boundary. So again, for the boundary condition, we have to find the boundary condition that is related to the velocity. Okay, so find the boundary condition related to the velocity. If we look at the phenomena here, at the surface of the solid surface, the fluid is no slip condition, so that means the velocity of the fluid will equal to the velocity of the solid. At that time, the solid is just stationary, diam. So that means the velocity of the fluid would be also similar to the velocity of solid, would be equal to 0. So here we can conclude that at boundary condition, which is when x equal to delta, which is on the surface, the Vz would be equal to 0. So by adding this one, we can write, for example, 0 equal to minus rho g cos beta divided by 2 mu plus C2. So we can get the C2 then, so the C2 would be rho g cos beta divided by 2m. Okay, and then we can put it back into the equation for the C2, and then putting like this, and then usually we the engineers, the chemical engineers, and also the scientists likes to rearrange the equation. Okay, so the equation that rearrange, so we actually should have Vz equal to this case, minus rho g cos beta divided by 2 mu x squared plus rho g cos beta divided 2 mu delta, that one, and this one is rearranged into this part. Okay, they basically try to take it out all of the constant out there. Okay, and then that will leave minus x squared plus delta square, and then they also take out the delta square, and then they make it something like this. Okay, so this tells you that at x equal to 0, the velocity has a number multiplied with 1, so that would be the maximum. At x equal to delta, which is this also become 1, so 1 minus 1 becomes 0, so the velocity would be equal to 0. Okay, and if you look at here, this is also quadratic equation, so it is follows the quadratic equation. Okay, so then we can see here that the final result for the following film problem showing the momentum flux distribution of the velocity distribution. If you look at here, the momentum flux distribution, the tau xz is 0 on the surface of the fluid the fluid there, and then on the surface of the solid it has a maximum value because it is a linear equation. Okay, so just rewrite here the tau xz equal to rho g cos beta multiplied with x. So it is a linear equation. Okay, and for velocity distribution, Vz would be if you can I think I can check that one there. Yeah, it's also a quadratic equation. And then you know it's a quadratic equation and it has a maximum value on x equal to 0 and then minimum value equal to 0 at x equal to delta, and then it is a quadratic equation. So when we want to make a profile, that is the velocity. Okay, so if you have a steady river or a laminar river like that, and then you measure the pressure, the temp, the velocity in this area, in this case, and then in the other case, maybe you can find quite similar result, yeah, with that one there. It had also been proved. And then what else that we can learn from the implication that we can learn from this case? We can find the maximum velocity at x equal to 0. So if you have a thickness of a falling film, we can of course it should be laminar and it's falling film, and then we can calculate what is the maximum velocity at x equal to 0, which is this one, rho g delta square cos beta over 2 mu. And then based on the calculus, you can also find the average velocity. So the average velocity is actually the Vz, and then it should be integrated with dx and dy like this, and divide by the dx and dy. So it's basically the velocity, it should be integrated with the area and then divide the integration of the area. Okay, and it's equal to 1 over delta from delta to Vz x, and also this is the Vz, and then let's take it out the constant there and then integrate this one, change the dx into dx divided by delta for to make quite similar ideas here. And then it will conclude into rho g delta square cos beta over 3 mu, that one. Yeah, so if you look at here, if this is the V max and this is the average velocity for falling film, the average velocity is the 2 over 3 of its V max. Okay, so if you can calculate the V max, you can calculate the average velocity. Actually, in pipelines, in fluid mechanics, the velocity that we actually use is actually the average velocity. Okay, but with transfer phenomena, we can find the profile of the temperature, which one is the maximum, which one is the minimum, and also which one is average. Okay, another implication, we can also, if we integrate that with the rho and also the mass, yeah, we can also get the mass rate flow integration of the velocity distribution and multiply with the rho here. So this is the velocity, integrate with the dx and dy, which is the cross-sectional area, and then that become a volume. Yeah, this become a differentiation in volume, and then multiply with the rho. So rho multiply with the volume is the mass rate. Okay, so volumetric rate multiply with the rho, but become a mass rate. And then here this is the mass rate if we want to calculate how much is the mass rate of the flow. And then in order we also can get the film thickness from the mass rate flow, just to change it. So if because we know that the mass rate is a function of this one, yeah, the function of the this is the equation. So if we know the mass rate, we can also calculate the film thickness. So how much is the film thickness required so this phenomena can be applied? Okay, sometimes if the flow is too thick, is too big, sometimes this principle will not be applicable. Okay, so this is how to calculate the thickness. And then the last one is to the force on the solid surface. So the force of solid surface is actually defined as the shear stress at multiply with the LW, yeah, multiply with the area. Okay, so they integrate the shear stress is integrate with the area, but with the differential to the y and also to the z. So we can write here. So that means the shear stress we have to integrate at x equal to delta. Yeah, so the shear stress at x equal to delta, which is on the solid surface, multiply with the y and the z, and then you can get this one. So if you're asked how about the force on the solid surface, then this would be the answer. Okay, I think that's all for that would be the end of this case for the flow of falling problem. I just want to make sure and then to give you a heads up on all of these steps is actually are gonna be questioned on the exam. Okay, so it's gonna be start from the where to put the coordinate points, yeah, the first one, and then you have to sketch them in 3-dimension and 2-dimension, and then the third one is to write the momentum balance, and after that you expand it, expand it, and after that to get the momentum flux, this one, which one, yeah, the momentum flux. Okay, and after that again get the velocity distribution as well. Okay, and after that you have to sketch this one. So all of this would be all the step by step would be questioned as well, would be asked in the exam. So I think because you have your 3 credits means you also have 3 hours to study at home. You can try to rewrite by yourself, rewrite this case, and then try to understand in each steps, and then by hand. Even for me, I also still writing, yeah, I'm still writing and then do it by myself, so I can understand all the steps if I can write by hand. All right, I think that's all for today. So we will have more times on Friday. For this Friday, we're still gonna be online. I think we're still gonna watch over it because the Omicron case is like very increasing. But I have reserve a room, the class for the next Friday. Okay, so not this Friday but next Friday. So if we can do it, if everything looks all right, and then let's have an offline on next Friday. So at hopefully at that time we can I can go around to you and then check one by one, something like that. All right, everyone. Thank you very much for your attention, and then I'll see you again on Friday.